Bismillahirrahmanirrahim. So we are back with our next class, that is the crystal field splitting in octahedral complexes. So crystal field splitting ये हमने last class में start किया था, where we discussed the basics in the crystal field theory. तो यहाँ पे हमने कहा था in nutshell कि bond between metal and ligand is purely an ionic bond. That means the metal and ligand, they are actually behaving like point charges. Point charges. So the bond is basically an ionic or electrostatic bond. Now we have a topic here, that's crystal field splitting in octahedral complexes. That means the complexes which are of this type, ML6. Central midline, and then we have 6 ligands. And octahedral complex means that we have a geometry where we have a midline at the center. 4 ligands are facing they are actually oriented. They get oriented along 4 corners of a square plane. Square plane here. And then one ligand is above this square plane and one is below. So that makes it an octahedral complex. Now, इस octahedral complex की formation कैसे हम understand कर सकते हैं with the help of crystal field theory? And then what is this crystal field splitting? Now, let us see. That means in order to make this 6 coordinate complex, that we have metal and 6 ligands are basically approaching, and then we have formation of ML6 complex. ठीक? Now ये जो 6 ligands है, as per crystal field theory, so they are either ionic or they are either neutral. So they are point charge, they have a charge. Metal ion, we know it's a cationic one. ठीक? Now, as per crystal field theory, during the formation of complex, the ligands approach the midline. So ligands approach the midline from 6 axes of a regular octahedron. Again यहाँ पे क्योंकि ज्योमेट्री जो है 6 कोऑर्डिनेट कॉम्प्लेक्स में जो प्रेफर्ड ज्योमेट्री है, जो स्टेबल ज्योमेट्री है, स्टेबल शेप जो ये बनाते हैं, दैट्स octahedral. That means, and we know in the octahedral complexes, all the ligands, they are oriented along the x, y, z coordinate. So they are oriented along the x, y, and z coordinate. If I say it is z, it's y, it's x. So they are oriented along the x, y, z coordinate. So यहाँ से ligand आते हैं, and one is here. This is actually perpendicular. On the back side of that, one more ligand approaches, one from this side, one from this side, and one from this side, and one from this side. So, and then we're basically considering the midline at the center. So when midline is at the center and 6 ligands are approaching it along the axis of the coordinate system, then it will result in the formation of this octahedron. Now, as per crystal field theory, जैसे ही ligands approach the midline, now we know metal ion has the d orbitals. And d orbitals, their number is 5. And we have dxy, we have dyz, we have dzx, then we have dx square minus y square, we have dx minus y square, and then dy square, and then dz square. So, आप समझ पास लगा? सबको पर, सबको 10 मिनट पर. So this is one set of orbitals. This is another set of orbitals. So the 5d orbitals, they can be divided into the 2 sets. First is this, so 2 orbitals, this one. So if we look at their maps, so dxy it looks like that we have x and y axis, and the electron density or the lobes of orbitals, they're actually in between the x and y axis. So same is the case when we have yz. So we have y and z, the lobes are between y and z, and then dxy, the lobes are between x and y. So all these three orbitals, they're having the electron density or the lobes, they're actually in between the axes. While in case of these two orbitals, for example, dx square minus y square, so the lobes are perfectly falling on the axis, number one. So the electron density is purely, that's the majority of the electron density is oriented along the x and y axis. And then dz square, we have, this is z, let us say this is x, this is y. So we have the shape like this type, and then we have some minor electron density in the xy plane. So that's the majority of the electron density is along the z-axis. So again the electron density falls, the lobes are falling along the x-axis, and in this case they are falling the x and y. So in this set of orbitals, the electron density is along the axis of the coordinate system. Now as the ligands, they approach the midline from along the six axes, so they approach the midline along the six axes. यहाँ पे थोड़ा दिखाना मुश्किल है, so this is a two-dimensional figure. So as they reach closer to the midline, जहाँ पे the midline, उसके orbitals जो है, there we know the midline is the d orbitals, and then we have some electron density there, and these ligands, they are either neutral or charged. So in both the cases, that once they reach very closer to this midline, and there the repulsion occurs between the d electrons, the electrons on this metal, and the ligand electrons, that's the lone pairs. So that repulsion is different in case of these orbitals, and it is different in case of these orbitals. Since these orbitals have electron density in between the axes, they feel less repulsion. So they feel less repulsion on the midline, while as they are oriented along the axis, and ligands are approaching to the central midline along the axis, so they are feeling the larger repulsion. So when there is larger repulsion, that means this set gets raised in the energy. इसकी energy increase हो जाती है, and this set gets lowered in the energy. So इसको हम ऐसे दिखाएंगे. So we can show it by this diagram. So initially, जब midline was it was free, so all the 5 orbitals, they were of same energy. So this is your dxy, dyz, dzx, dx square minus y square, and dz square. So they were of same energy, so they are said to be degenerate orbitals. So they are degenerate because their energy is same. All are of same energy. But so this was the case when we have a midline present. Now during the ligand formation, when the ligand approaches the midline, we have the complex formation. This type of situation exists. So this type of situation exists. So we have the two orbitals are raised in the energy, that is dx square minus y square, and this is dz square. And those orbitals are lowered in the energy, they are dxy, dyz, dzx. So this is the center of gravity, where we'll assume that the energy is 0. So we assume that the energy is 0. So these are lowered in the energy, and these orbitals, they are raised in the energy. So they are raised, since they are facing directly the orbitals, so this energy gap is more, and it is 3/5. So this is less, this gap is less. अब यहाँ थोड़ा सा बनाने में इसको थोड़ा सा हुआ है, so इसको थोड़ा सा ऊपर बना लेते हैं, because this gap is less compared to the other one. Okay? So this gap is less and this is more. So this is your so this is 2 by 5. Fine. So 2 by 5, that is equivalent to 0.4. And this 3 by 5, that's equivalent to 0.6. So that's clearly more. So it gets raised more and they are getting lowered less. So this is called as this splitting of d orbitals during the complex formation. Once the ligands approach closer to the midline and they form the complex, the result is that there is splitting of orbitals. So this splitting of these two orbitals, this is called as crystal field splitting. This is basically called as crystal field splitting. Now since this is an octahedral complex, this is designated by delta 0. So O stands for delta O, octahedral. So this delta stands for energy. This is called as a crystal field stabilization energy. So this is called as CFSE. So overall the complex gets stabilized because of this splitting. So this is called as a crystal field stabilizing energy in the octahedral complex. So we can show it by delta 0 or delta O. Now this delta octahedral, this is equal to 10 dq. So we can express this as 6 dq and we can express this as 4 dq. Okay. So this is basically the main diagram as far as the crystal field splitting is concerned of the octahedral complexes. So this is basically ML6. That is complex, and this is. So this is all about the basics, and the rest we will see in the next class. So this is basics about the crystal field splitting in the octahedral complex.